So today we're going to dive deep into build systems. So this is basically the last lecture on tools. So this spot is reserved for C++ topics, like these Wednesday lectures. But the first two lectures were about tools like Linux. Today it's gonna be about build systems. So sorry, because last lecture was like a bit longer. This time I will try to make it into 1 hour, so we all can pay attention within this hour. And basically, starting from next week, we will be discussing C++ topics, and all the tools topics will be discussed in tutorials and offline videos. Okay, so this is like an important deal for me. So because most of the people I've met that they struggle with C++, C in general, this struggle is usually related to build system. So for me, it's really important to understand the concepts behind building programs and actually how to deal with build systems. So we are not going to see any C++ code in this lecture, so I'm sorry for the ones that really want to start doing C++ coding, but in this case we will basically take a step back and then learn how to use the tools before we start coding. Okay, so this is basically a really brief of how it looks like a software development ecosystem. So in the middle we have the source code. So usually when people think about coding in general, they will think about this particular thing. So you only focus on source code, but actually if you pay attention to the picture, you will see that there's a lot of other tools involved in the development of this software. So it's not just the source code you write. And basically, learning how to deal with these tools, learning how to use these tools will give you superpowers in terms of like how to work with C++ and any other language in general. So in this particular course, we will discuss some of these tools, but not all of them. So today's lecture is about build systems. So this will give you the idea of how to build C++ projects, and then how to avoid some errors. Also, during tutorial times, we will discuss a bit, but we will not dive really deep into how to use linters, how to use static code analysis to improve your code. Of course, this is a big topic nowadays, and we will all have a separate tutorial for testing. Also, there are like some formatting tools that will format your code like automatically. Nowadays, CI and CD, there is basically continuous integration and continuous deployment, is a big topic like in all software industries, including robotics. So this wasn't true probably 5 years ago, but now it became the standard also in robotics industries. We will not see any tutorial unless some of you guys say, okay, no, Nacho, I would really like you to make a tutorial on this. Then probably like reaching the end of the course, we can make a small tutorial on CI and CD. Something that you will be struggling with a lot, probably, it's gonna be Git. So this is the version control system that nowadays everyone uses. So basically, again, we will not probably do like a full lecture on Git, probably a tutorial. So I have some recommendations, but you will need to use it. Also, we will have a small tutorial on how to debug projects, C++ project, and there are all sort of things. The important thing I want to mention here is that all the stuff you see here, they are tools. So for me, when you are working on C++ projects or software projects in general, they're like two different distinct things. So one is the tools you use, and the other one is the concepts. So usually for me, it's better that if you invest time focusing on concepts and not tools, because the tools will change in 5 years, but the concepts are very unlikely to change. So whenever you need to make a decision on where to spend time, probably it's a better idea to go for the concepts. But anyway, C++ in general is a complex language, and we need tools to work with this language. So if you only focus in the concepts, then you will struggle a lot trying to apply these concepts to real source code. So basically, the tools will give you superpowers in terms of what you can do with these concepts. And as I always say, if your tool sucks, you most likely will suck. So it's never a bad idea to spend some time trying to improve your tools or to make a better usage of it. So today we're gonna be diving deep into build systems and how the compilation process works at all. So the compilation process. What is a compiler anyway? So a compiler is basically a program, but it's not any program. And it's basically the guy who will transform your horrible and unreadable source code into binary code. Binary code is the language that the computer can understand. And here's a picture like showing how this process works in a really high level way. So basically you will write a source code saying, I want the computer to do this. Then there's this guy called the compiler that will do real black magic, and then you will turn this source code that is readable by humans into binary code. And this binary code is basically the one that the CPU is happy to eat. Let's put it this way. So the easiest way you can compile a C++ program is basically just calling the compiler. In our course, we will be using clang. And this will basically build a program. They will put, the compiler will use the a.out name, that this is the standard. And then this program, if everything is working, this means that the compiler is properly installed and all the system libraries are there, then you're ready to go. That's the whole thing you need to know about compilation. This is something that we tested on previous lecture on the Hello World example, and I guess that all of you already did a small example on this. And then the question is, will it be always this easy? Of course not. And this is a big thing, and something I forgot to mention is that I also have another say, that is that if you want to understand a project, then the best way to understand it is through the build system. Basically, I met also a lot of people, both in academia and in this industry, that they struggle a lot just because they don't know how to deal with build system. And it's not because they are stupid or they are not smart. It's because probably they didn't spend the time trying to understand the build tools. And this also gives you some insights on how the project is structured and how it really works. So basically, knowing a build system of a project is a really good idea if you want to get into the project. The compiler, so whenever you call this clang ++ main.cpp, will basically execute 4 steps behind the scenes. One is called the pre-processing step, then it's the compilation, then the assembly, and then the linker. So if we try to make a diagram out of this is basically what is happening whenever you try to compile a C++ program. All these steps are like really, so we can dive really deep into those steps, but I think it makes no sense. But it's really good for you if you really know what's going on behind the scenes whenever you try to compile something. And by the way, when you learn how to build programs, this is also a superpower, because it will give you the ability to understand how to do things without having to like do random steps, without knowing anything that you're doing. And once you understand how to build the things, then you know your program, you know your project, then you can deal with it and you own this project. You can change it the way you want. So a lot of people usually write everything in one file. Let's say, okay, my whole project is called big project.cpp and I have all my pipeline there because I don't know how to use this include statements and whatsoever. So the idea is that if you know how to work with the tools, then your life will be easier. Okay, coming back to the lesson. Basically, whenever you call the compiler, you invoke the compiler, you will give a source file. In this case, it's called main.cpp, and then the 4 steps we mentioned will happen behind the scenes. Let's see, like step by step. So this is a small example we will do. This is something that you can do it. I will actually recommend you to try it on your machines so you can get some insights of the compilation process, but this is not something you do on a daily basis. Okay, let's try the trick. It's working, amazing. Okay, we have a terminal here, and then let's try to do this compilation step by step but manually. For that, I will go to my dev directory and I will create a directory called compilation. I will cd into this directory, so this is where I'm actually standing right now, and then let's remove everything from here so we have a clean working directory. So the first thing we will do is we will create a really small program, because we don't want to focus on C++ on this lecture, but on how to build C++ projects. So I will not use the Visual Studio Code Editor because it's way too much for doing this. So let's call this main.cpp, and then let's do what we already know how to do. Let's create the main function, and then let's do cout log build system. Oops. And then this guy, and then we return 0, and then that's basically it. So of course, if you do clang ++ and then you invoke this compiler with main.cpp, now when you do ls, you will have this a.out, but this is basically all you need if this program is super simple to compile. So let's remove this for now, and then let's start with a clean working directory. So the first step is pre-processing. This is basically so we discussed this on previous lecture. So whenever you have an include, so in this case will be this guy. So whenever you do whenever you include a file in the on the source files you're talking about, basically who is in charge of like going to this file and copy pasting the content of this file on the main.cpp file? This is a preprocessor. And also we'll expand macros, we'll remove all the comments. So let's do main.cpp, and then let's put here, this is a comment where it is, right? And then the preprocessor will delete all the comments, will include all the her files, and will expand macros. You don't really need to know how to use the preprocessor nowadays, because actually the only thing you care is like how to include directories. If this would be a C class, then we will be using macros. That is something really ugly to use. And if I find macros in your code, you will struggle, my friend. So I don't want to see these defined macros. But basically the preprocessor is the one in charge of doing this. And then if we invoke the compiler, we can say, okay, I want to do the steps manually. Perhaps because I want to check what's going in between, or because I want to change something else. The flag you need to pass to the compiler is this big E, and then you do main.cpp, and this will open the file, preprocess this file, and then output the results to the standard output, right? So if I do this, you will get boom, a lot of stuff. But basically, let's redirect the standard output as we did on the first lecture, and then let's call this file main.i. This is like standard on the community. And now we can actually open this file and inspect the contents. So if you try to see this, you will see a lot of stuff that this all actually comes from the IOStream header file. So all this stuff, we didn't write this code, but basically it was part of the standard library. So there are a lot of lines actually. So let's go to the last line. And if you see here, so this small example, after pre-processing, we have 28,000 lines. And our original code was basically nothing. But all these lines actually came from the include IOStream header file. And if you see the source code, you see that, for example, our comments is not there anymore. If you remember, like this is a comment where it is, it's not here because the preprocessor like clean up all this stuff. And whatever is up, basically, also the include is not here. So the include IOStream is not here anymore. Let's check again our CPP example. Basically, it was an include, then a comment, it's not there anymore. Okay, so now it's time for compilation. So this is a term that we all use wrong, including myself, but it's fine, like everyone knows that it is like this. But whenever you say I will compile this program, you're basically doing I will pre-process this program, compile it, assemble it, and then link it to create an executable. But basically the whole compilation process, there is one step that is the real one that we call compilation. And this is basically where the compiler starts to works for real. I mean, like this is, if you want to write a compiler for any language, this is your task. Basically, once you have the pre-processed file with all the source code, then you need to somehow figure out how to translate this into assembly code. As you remember, in the first lecture, we saw like some really ugly assembly example. It's not something that we will discuss in the lecture, but basically, you need to know roughly what it is. Okay, so you have the preprocessed file and then you need to compile this to generate assembly. So basically how you do this, you invoke clang++, and then you say, okay, this is my source file, right? There is a warning, but basically if you list your directory right now, you have a new file that is called main.s. Again, if you open this file, then you will see assembly code, that this is not something you can actually understand right now, unless you have a like electronics engineer background. But basically, this is what it's really easy for a machine to understand. Then the third step will be to, okay, now that we have the assembly instructions for this particular target, that is a Intel CPU, now it's time to generate like an object file. Basically, an object file will be no more than binary code that a computer can understand. And I will stop there because otherwise this can take a lot of time. How will you do this? Then we again refrain clang++, and then -c, and then the assembly file. Now, if you list your directory, now you have like 4 files: the original file, the main.i file, that is a preprocessed file, the assembly file, and the object. Of course, if you pretend to open this object, you won't see anything because this is binary code, and actually it's in ELF format. So you can actually see some strings between the thing, but there is basically, it's not understandable by a human, but for a computer. But of course, if you want to try to run this, it's okay, this is my program, it's not enough. So the last step is to link. So how we link this program? It's super easy, just do clang++, and then you say, okay, this is the object I want to link, and then let's call the executable, so the output of this linking process. Here you can invoke multiple object files. In our case, we only have one. Let's call it main. And then if you list your directory, you have your main executable, and finally you have the executable. So, doing a recap. Basically, whenever you want to compile a program, you should be using like doing 4 commands. Hopefully it's much more easy, but this is basically what's going on behind the scenes. And if you want to do clang++ and then main.cpp, that is the simplest one. Basically, all these steps are happening, but just behind the scenes, right? Also, something that is super important is compilation flags. So probably I will do a tutorial on this because I really want you to know how to use, in particular, this guy, how to optimize your code. But basically, whenever you compile programs, you can actually specify different flags for the compilation process. And one of the options is like, okay, the standard. So as we already mentioned in the previous lecture, whenever you call clang++, you have a default standard, but you can use like C++11, C++14, C++17, 20, 23, depending on which standard is supported by the compiler. In our case, C++17. And also, for example, you can have additional options like, okay, if you have any warning, just show it to me. This is basically all. This is basically, if you find a warning, just let me know. Extra is like, if you think that there is another warning, just also let me know. And this error, it's warning as error. Basically, you say, okay, if you find a warning, just stop the compilation process. Something is wrong for me. But this is something that you pick, actually. The optimizer basically is one of the most important things in the compiler. And a good compiler basically has a good optimizer, and this is basically the steps involved that will turn some source code into really optimal and fast code. This is basically, let's pretend that you have to do some operation like 2 + 2. Let's keep it simple. You can do it at runtime, and this means, okay, you can generate these two numbers in memory, then go and add these two numbers in memory and then get the result. Or you can realize that 2 + 2 is a really simple computation to do, and you can do it before you run the program. We will discuss how to do generics programming and static code generation on the last lecture. So this will happen in 2 months, or in 8 weeks, so just wait for it. The only thing I don't want you to forget is that there is a way to compile your program and add optimization to it just with flags. Okay, so now that we dive deep into how to compile a really simple program, now we need to use this in our advantage, and then let's talk about libraries. As usual, before I dive deep into this, I will give you 1 minute for questions, otherwise we continue with the lesson. Okay, no questions, so let's continue. What is a library basically? So now that we know how to more or less build programs, the idea is that we want to make usage of the compiler and the linker and all the tools in the tool chain and build really nice projects. So basically that's where the concept of library comes. Instead of having everything in one source file, we want to say, okay, I want to put all these symbols, let's say like they are arithmetic operations, in one library. And basically a library is just a bag full of symbols and implementation details. So why we use libraries is because it's much easier to maintain, it's much easier to distribute, and it makes your project easy to read and to work with. So a library, it's basically multiple object files. These are like the symbols that are logically connected. And there are 2 types of libraries. Most likely we will be only dealing with static libraries, that they are faster, but of course they will take more space because they become part of the binary. So whenever you static link a library into your program, you basically have your program and all the symbols from the library all in the same executable. Of course, if you have like some restrictions, like an embedded platform, this is not the best idea, because probably you have like a 2 GB binary and probably you don't need this. But of course, it's a bit faster than doing dynamic libraries. But basically the dynamic library is what you have installed on your system. So if you go to the /userlib directory on your Linux computer, you will see a lot of .so libraries. That basically these libraries are sleeping there at runtime. When you need a symbol, you will go and search for it there. Basically, static libraries are just like an archive. So basically you have a bunch of symbols and then you put it all together in a .a file. How to create libraries in C++? Basically the mechanism to do this is splitting the declaration of a function and the definition. So for now we will stick with functions. We will discuss a bit more about the syntax of this next lecture, but believe me, for building C++, you don't really need to know C++, just for building. So all these concepts are related to build systems. So don't worry if you don't understand something from the code, because the idea is that you shouldn't be paying attention to the source code right now, but to the build process. So basically, a function declaration sets up an interface, and this is basically, let's call it a promise, and the one in charge to search for this declaration is the preprocessor. So whenever we will discuss this in 2 minutes. And the function definition, it's basically the implementation of this function. So whenever you work with you want to create libraries, then you will declare your functions in some header file, most likely. And this is basically you're telling the preprocessor, okay, I promise I will give you the implementation for this function, so don't worry, you will get it soon. But then you just put the interface of the function. In this case, it's a function that's called funcName. It takes an integer as input parameter and it returns void. This means nothing. And then in a different file, the idea is that you write the implementation with all the details of this particular function. How we split this between files? So usually you will have some header file where you only put the interface, and how you specify function definition. This means interface is basically this guy, and how you specify this is way too big, still big, with this semicolon. So this basically says, okay, there will be a function, there will be an implementation for this function, believe me, it will happen at link time. And then of course you need to write implementation of this function in some other file. And so actually, yeah, now this is fine. So this is the header file, it's called some file hpp, change the color, and this is the implementation for this function. And then you need to retype the prototype, so you tell the compiler, okay, here's the implementation, and then you basically say, okay, blah blah blah, and then you put the details. And then, for example, in your main program, the only thing you need to know for now is you need to include the header file. The header file holds this promise I'm talking about, that is basically the function definition, but not the implementation. And then you can use this function without any problems. If you want to build this, and you should do it in your home, just write these 3 files. You can pick the names you want, and then you try to compile it, just saying, okay, clan++, and then program, blah, blah, blah. But then you will get an error. But it's important to know that this error will happen. What happens if we put implementation also an HPP file? We need probably 1 lecture for discussing this on where to put stuff. But basically, if you put implementation on header files, the simplest thing that you will do is you will pay the price at compile time, because you will basically, whenever you include this file in other CPP file, so the question is like, what happens if instead of let's do red. This is not red, I'm colorblind. So let's say, okay, I want to put all my implementation on the HPP file. Of course you can do it, but you need to really know what you're doing, because whenever you include this file, you will basically copy the whole implementation, and then you are basically not using the linker, and this way your build will be super slow. Of course, if you're working with 1 file, then it will be fine. But whenever you work with like billions of files, you can actually run out of memory on your build machine when you try to build this. So whenever you do this, you're basically not using the linker, and then you're basically throwing away one of the tools you have on your toolchain. So knowing how to split this implementation, basically it makes you friends with the linker. So, okay, if you want to build this small example, then we will have an error, and the error is super important to know that the error is by the linker. So what is the meaning of this? when you try to, so if you want to go for the 4 steps and then you do this, but instead of doing the whole thing at once, you do just a pre-processing part, then this will work, right? Because whenever you include the file, let's go back. So when you include this here, the preprocessor will be happy enough because he trusts you and say, okay, there is some function that the linker will give me the implementation in a future time. This is at linking time. So basically, you can go up to step number 3 on the compilation pipeline without any issues, right? The thing is, when the linker gets invoked, and then it will try to search for the symbols from this function, it will not see the function. Why is this? Because the implementation are not there. So if you see the compile line, basically you're just using the program.cpp and you're not including any information about the other .cpp file. So that's the idea of the linker. So basically, if you see the original picture, so the last step on the compilation pipeline, it's the linker, and it will basically, with the promises of the functions you have made here at this part, that is basically just the function prototype, the interface here, it will go and search through all the object files. That can be object files, libraries, could be external libraries, for example. And then it will say, okay, here is the implementation for this promise, some function, and then it will put it into the executable. And basically, that's how you link an implementation of a function with the definition, right? So that's when you don't use when you put all the implementation on the header file, you're basically skipping this step, and then you're basically not using the linker. And of course, this can hurt you in many ways, but the easiest way to put it is like, okay, compile time will be super big and probably would fail because of you will run out of resources, right? So the library it's a binary object that contains the compiled implementation of some methods. In our case was some func, the function, and the linking process will map a function declaration that is basically the prototype with the semicolon to its compiled implementation. Basically, to use a library, you need 2 files. The header files we have where you have all the function prototypes and the interfaces, that is this promises, and the compiled library object. If let's say if I want to give you a library and I don't want to share with you the implementation of the library because I know I want to sell this library to you, the only thing I need to give you is like the header file where all the functions prototypes are specified, and the library object, that is all the binary code. Of course, you can do reverse engineering on the object files and the library files, and then try to figure out like what's going on. But basically, if I don't give you the source code, then you don't know what's going on. It's just like binary objects. So whenever you install, for example, NVIDIA drivers or any other proprietary software on your machine, this is basically what is happening is this. You're getting a header file, or actually multiple header files, and library objects. Okay, so how to build these libraries? I think we have time to do a small example. So basically, let's pretend that you want to build a library. It's called tools, the library. In this case, we'll have 2 functions. It's called make it sunny, make it rain. But basically, for now, we don't know the implementation. So this is just the prototype. And then for that, we will create this tools HPP file. And then we will specify the implementation on the CPP file. So let's do this example right away. So let's go to dev, and then my first library. Okay, clean working environment. And then for now, let's do this touch command will create these files but empty, and then tools.hpp, right? So this is all we have, and then let's open now Visual Studio Code so we work more comfortable. Let's change this, make it bigger, and then let's start with the library. So this is will be the header file for our library, and then we'll call pragma once here. This is basically to avoid including this header file multiple times, and then here we'll do okay, make it sunny, and then the function is make it rain. So was that the name? Make it rain, make it sunny. Yeah. Okay, so basically this is the header file. This is the prototype of the function, but the implementation is not here. For that we will open, then let's do this on the side, and then here on the CPP file we will do include, and then tools HPP, and then let's copy this here basically, and then how we implement this function, basically opening the scope operator, and then let's include IOStream, and then here it's now sunny. And this is the implementation. Let's, they're way too easy, so the formatter is doing its job. And then let's do see error, and then oops, not yet implemented. I don't know, whatever, implemented, right? And then don't forget the semicolon, and put this here. And this is basically the implementation. So if you go to the slide, this is basically the example. There are the implementations are here, and then whenever you want to use these functions, then you will need to include just the header file. So let's put this here, and then so let's include, and then it's called tools.hpp, and this basically you're now copy pasting this on this these interfaces on the .cpp file, and then let's create a main function, and then now see out, and now we can actually make it rain. We can call these functions and make it sunny, right? Done. But now if you want to build this, so okay, let's close this guy here. Oops. And actually let's close this. If you want to build this, so these are your files, then you will do clam++ and you do main.cpp, and then you get this linking error, right? Linker command fail, blah blah blah. Why is this? Because you have the promise, but you don't have the implementation. So how to build this? Let's do it by hand really easily, because now we gain this superpower that is to build libraries. But now we have another problem, that is that we don't know how to to write libraries to make our life easier, but we don't know how to build it. So basically you will need at least 3 steps. The first steps will be you need to compile the implementation of the library that is on tools.cpp into an object file, and for that you will use this guy, that if you remember, it's part of the 4 steps of the compilation, and that's why we saw it before. And then you will need to create this library object, that this is basically with the archive command. and you can use as many object files here as you want. In this case, we'll have only one. And then whenever we compile the main.cpp file, we will say, okay, also please link to this library. This is where the symbols are defined. So let's do it let's try to make it work. And then let's open tools HPP. No, let's keep it like that. It's fine. So we say C++, and then you say, okay, standard, not this standard, it's C++ 17, and then we will do tools.cpp, and then the output file, let me check, it's tools.o, and because I'm missing the dash C. So if you see here, don't forget this, because now you're basically trying to make an executable. So C++, and then dash C, and now you have an object file, right? Again, if you want to open this object file, there's nothing here, but there's a command called the nm that you can demangle the symbols in here. You don't need to know this, so I'm just showing you to show that I know it. Now you can see what is inside here, and these are all the symbols. But basically now you have the implementation, that is the tools.o, with all the binary code for this library, and the header file with the declaration. Now you need to create an archive. Actually, in this case, it's basically R, and then let's call it libtools.a, and then we will put this into the archive. If you list the files here, you have now this library that is nothing more than the object, the definitions on the tool library. And the last step will be to compile this guy, that is basically the main file, but saying, okay, now you're telling the linker, search libraries on this path. This is the big L and the dot, and the library you want to link is tools, right? And then let's call this main, and indeed it worked. I'm going fast because I'm really slow, so let's try to fit this in 1 hour. Now if you run this program, you have all the implementations details there. Anyway, basically this was really painful to do. So we have only 3 files, 4 commands, a lot of stuff. And that's why we should, as humans, we should pursue better tools, right? It's impossible that you can actually build real libraries with much more source code and make it rain on sunny without any real tool behind you. So building by hand was hard. We had 4 commands to build really simple hello world example with just 2 symbols. And actually this is the first exercise of task number B on your homework assignment. You need to do this by hand. And then how does this scale on big projects? It's basically impossible to maintain because you cannot like run 50,000 commands for all your libraries. And that's why humans invented build systems. What are build systems? Just more tools, right? There are many of them, like way too many probably, especially for C++. And the idea behind this is that they will automate the build process of your projects. The brief history is that they begin as shell script. So, okay, you can say, you just run 4 commands. You can write a shell script and then you just copy paste your commands there. That's your task for first assignment. But then of course, if you change the name of the file, then you need to go to the shell script and change all the naming. It's a mess. And then they turn these shell scripts into make files. That is basically one of the first build systems that is still nowadays one of the most used. And then they say, okay, but make files are really hard to write and maintain, so let's create meta build systems like CMake that basically will generate make files for us, right? And the fact is that CMake is not a build system at all. It's basically a build system generator, so it's called meta build system, and it will basically generate a build system for you. After you use CMake, that is super popular nowadays, you need to use an actual build system like Make or Ninja, for example. So what is the idea? What I wish I could write. So we have these 3 commands that we just run in the example, a bit faster probably, but you can go into the video and do it slowly. Of course, you should try all these examples on your computer. And then I would like to write the script in the form of, okay, this command that is long and boring. The only thing actually these 2 commands, I actually want a library. So, okay, just put add library, and then let's call it tools because that's the name we pick. And then just build objects for tools.cpp. If you have more files, you will put it here. And then I want an executable that is basically, let's put it with other color. This is too fancy, I like it. This guy, and it's main.cpp. So actually this is the first part of this line is this one. And then the other thing you need to do is like us is saying, okay, link this binary to the tools library, right? So all these 3 commands are full of information that we don't want. We actually, the only thing we need is like add library, add executable, target and libraries. That's what I wish I could write. And then that's where CMake comes into the game. So one of the most popular build tools out there does not build the code, we already say this, but generate files to feed it into the build system. It's cross-platform and it's very powerful if you know how to use it. And still the build recipe, that is basically this build script, is readable. So if you see this, the add library blah blah blah, then this is still readable. So if you read the script, you can make a sense out of what's going on. But if you compare these 3 lines with the 3 lines above, then if you don't know a lot of compilation commands, then actually when you read these 3 lines, you have no idea what's going on. So that's the idea. That's why it's powerful. So from a user perspective, once you build this build script, the only thing you need to know is like the usual process is to create a build directory, and then you will execute CMake, and lastly you will do make. So basically this step here is because CMake is not a build system, so it's basically a build system generator. So the first step is to create the build system, make for example, and then make. All the process is completely defined on the CMake list file. So this is how it works, and all children's files, like if you have like multiple CMake lists on your project. Let's do the really basic first CMake project here, and for now we will reuse the example that on the make it rain and make it sunny. So let's go for it. I think we still have time, so yeah. So first let's remove .o and .a, so we have a clean directory. Let's create this guy, CMake list txt, and now let's open the file here. So the first thing you need to know is so there's some boilerplate code, but it's basically 2 lines. There's CMake minimum required, and then you say version 3.1, that is the one on my system. So in my case, if I do this, it's 3.10. Let's do that like this. And then you will need to specify the project name. So project, and then you say first project, it's on the slides. And then that's basically it. That's all the very basics you need to know. And then there are other stuff you can do. For example, you can do set and then CMake standard, and then you say, okay, 17, this basically replace this on the build flag, C++ 17. So, but this will do it for all the files. So if you have like 50,000 files, it will add this flag to all the compilation lines for all these files. If you want to do it manually, then you need to write it on all your lines. And then let's do add library, and then we call this library tools, and then this is the implementation, and then add executable main, and it's called main CPP, and target link libraries, let's link main with tools, right? And lastly, but not least, let's do this. So CMake. So this is important for all the toolings we will be using on this particular lecture. So this will generate a compile commands file that is a JSON file with all the build script, and I will show you why it's important in the tutorials, but now we will inspect this file. So okay, this is my first library. The first step is to create a directory called build, and then we will cd into this directory. It's now clean, and then we will invoke CMake. Then you need to specify ... because you're actually saying, okay, my CMake list file is on one level up. And if you see the output of this, you will see a lot of information like, okay, we found a compiler that is Clang 10, that is the one we are using, and some other stuff. So this is basically now ready to build. So if you do make, it will basically build the project, and now that you know all the steps involving compilation, you can actually make a sense out of this output. Now it's building a C++ object, you know, a .o file, and then linking a static library, lib tools. This is basically the second command we ran before, and then it stopped there, and then we will start working with the main. We will build the object main.o, and then we will link this object with the other library, right? And then build target main, it's ready. So if you list now, you have this file main that is basically the same object, the same implementation, the same executable as we did before, but much easier, right? And CMake export. And this is the thing I wanted to show you. If you inspect this compile commands.json, you will basically see the commands. So in this case, it's roughly equivalent to doing a shell script, but it's good to inspect these files to realize that they're actually doing the same thing as we did before. So there's no real magic involved in build systems, but they're like just script and steps that will generate the build lines for you. In this case, it's called in C++ with the standard, this is 17, is the same. And then it will, this is the file, and this is the object file. So if you compare this with the information on the slide, you will see that there is basically the same. And some other stuff you can do is, for example, it's like set CMake C flags. Oh, CMake. I forgot the. Sorry, let me. Okay, CXX flags. CXX flags, and then you can do, for example, all. And just by doing this on the build script, when you we will not even compile this. So when you inspect the compiles command.json, you will see that this WL is added to all the lines. So that's why for me it's important that you roughly know what's going on behind the scenes, and that's why you should run the 4 steps on the compilation process and build the libraries by hand the very first time. Going back and almost finishing. So now we have the libraries, we know how to write libraries, we learn how to basically split the implementation and the definition of functions in order to build libraries. We are using CMake to simplify the build process. And basically there are some other examples here on what you can do with CMake. The idea is like, it's not nothing that I can teach you in a lecture, but you should actually, of course, start working with it. And that's why homework assignment has an exercise on CMake list. So you should go there and check it out. I put you some useful commands here. The only thing I want to mention is that basically, if you really mess up the things, the good thing about CMake is that with this framework, you have a build directory where all your files are there. And let's say there is something that is not working, you can just remove this directory and then start from scratch. So in my case, so let's say that, I don't know, something is wrong. One thing I can do is just remove the complete directory, and then I do it everything from scratch. So take directory, and then directory cd into build, and then CMake ... And this will basically do everything from scratch, and then just you can make the project again, right? So make sure that if you're really struggling, just remove the build directory, and then that should be it. So let's do one thing, because I want to really stick to the hour thing, and we're basically done. Slides will be on eCampus. Here are some information on how to use CMake in your benefit. So how to find other packages on the system. So just make sure you go through it. You don't need to know how to use this now on CMake, because you are not using external libraries, but you will. So for example, when you do your final project that you will be using OpenCV, for example, then you need how to know this. That is basically one command that is called find package. So that's the idea of CMake. If you want to actually use libraries on your build commands, then you will need to specify all the paths manually, and this is a mess. And basically CMake will give you the tool to just run find package. That is this guy here, and will do all the dirty work for you. So there's no need to discuss this in the lecture, so I will just stop here. And okay, time for questions. We have some more minutes. Let's do recap. So compilation process, there are 4 steps involved. Then we saw libraries, how to manually build libraries, doing compile lines by hand was painful, and it took a lot of time. That's one of the reasons we are reaching the hour right now. It's because it takes time. And then we say, okay, instead of doing everything by hand, let's work with build system, and we introduce it CMake. And then we saw that with really simple with a really simple scripted language like CMake, you can generate your build systems and work much more easy. So any questions so far? By the way, the only way of learning CMake and all this stuff is just using it. So it's not, that's why for me it's not really on the concept side. It's just a tool, and you will be using this for your homework, the first homework, and probably the rest of your homeworks and your final project. Okay, so there is a question that is types of linking libraries. What do you mean with types? So basically you only have 2 types out there. It's called static libraries and dynamic libraries. So where is this? So here on slide 15, we have like basically the definitions. You don't really need to know a lot about this because it's not necessary, but the only thing you need to know that there are 2 types. The static ones will have everything packed, so it's like basically just a bag, so there is no real thing in there. And then you will put this library into your binary and make a big thing, and that's your whole program. And then the dynamic libraries, they're called dynamic. Actually, this is important. So whenever I say static, the thing that it should come up into your mind is basically something that will happen at compile time. So before, it's something that is happening before you even get to run your program. That's static in C++, let's say. So static linking basically say, okay, this is happening before I run the program. Okay, so this guy is telling me that I will put all the library objects into my binary. And dynamic, whenever I say dynamic, and this will, so we will reuse these concepts a lot during the lectures. It's something that is happening at runtime. This means I am already running my program. So for example, you're doing ./main, and then the execution start, and then whatever happens here, it's called dynamic. And this means if I have a shared object, a dynamic library, I will go and search for the symbols, the implementation of this library at runtime. This means, okay, cout whatever, and then make it sunny. And then in this moment, I need to go to the file, say, okay, let's search for this .so files, and then give me the implementation. That's why you can also have linking errors at runtime. So if you do this, and if you have time, you can actually do the exercise. Just use CMake, it's easier. Make it a shared object, and then remove one of the implementations, and then it will build this time. So whenever you forget to do it at static, with static libraries, then you get compilation errors, but with dynamics, you will see the same error, but at runtime. So that's basically the difference. So Andrew, probably that we can discuss it offline. So there is private public for this hero way of linking. Yeah, that's probably a bit deeper, but I mean it's a good question. So we were at here. If you want, if you want to use external library, do you have to compile it? It depends. So depends on the environment you're using. So if you're using pre-compiled libraries, so it really depends. So you can be using a package manager, for example, like Conan, and then this will download pre-compiled libraries for you. And the only thing you need to do is to specify where the library and the header files. But probably the other thing you can do is like, okay, you compiled it before. So this is how we will do it for OpenCV. We will download the source code, we will build it, we will install it in our systems, and then you basically specify, okay, just go and search for OpenCV, and you can actually include libraries as part of your build system, and this is actually really common, and then you build it with your program. So let's say you have a project, and instead of searching the system-wide OpenCV, you just clone OpenCV and build it before you even get to build your project. So this is actually quite common nowadays. Okay, in the meantime, so Git is something that we will probably not cover during lectures. So it's really important for me that you get started with Git. Git is a tool. Everyone needs some time to get used to the tool, but there is no real black magic behind. The only thing, it's impossible for me to understand how to use the tool if you don't use it. So the concepts behind are like super abstract, whatever, and then when you get to run the commands and use the tool, it's super easy. So my recommendation is just go, there's a 100 seconds get started video with some of the details, and just start using the tool. Also, Andrew, one of your colleagues, recommended this introduction, so it's a 15 minutes introduction. I watched the video, it's fine. Okay guys, thank you for your attention. Thank you for asking questions in the channel. If there's something that you want to discuss offline, Discord channel, email, I'm always available. And that's it.